Hello learners and welcome back to VLSI Simplified. In the last few videos, we explored what Verilog is and how it describes circuit and various abstraction levels. But now it's time to move from theory to real code. In this video, we are starting the real journey of writing a Verilog code by understanding the basic code structure and how to define modules, how to use ports, and how to reuse modules through instantiation. This is where Verilog truly starts to feel like a powerful design language. And don't worry, we will take it step by step with a simple examples to make it super clear. So if you are ready to write your first Verilog module, then let's get started. In this video, we are going to understand the code structure of Verilog, the foundation of all digital design. We'll start by learning how a typical Verilog file is written, like what components it includes and how they fit together. From there, we will dive into the heart of Verilog, that is, modules. So how they are declared, what ports are, and how we wire them together. By the end of this video, you will be able to write and structure your own Verilog modules and even reuse them in hierarchical designs using instantiation techniques. Alright, this is VLSI Simplified. Let's get started and let's simplify.
Feel me like a Hellcat.
Before jumping into Verilog modules, it's important to understand the basic anatomy of Verilog code file. So a Verilog design starts with a module declaration. This is your design block like a building unit. So it then defines a port list which includes input and output pins used to communicate with other blocks. After that, we declare the ports and write the internal logics. So this is where you describe what the module does. Finally, we close the definition with the end module keyword. So in summary, Verilog code is very structured. It's like defining a black box. So input comes in, logic happens inside, and output goes out. And in the upcoming slides, we'll break down each of these sections in detail with examples. Let's take a deeper look into what a Verilog module really is. So a module is much more than just a block of code. It's a design unit that encapsulates a specific piece of functionality. So think of it like a hardware component with well-defined inputs and outputs. It is the smallest unit of hierarchy in Verilog, and it allows us to build large systems by breaking them down into smaller and reusable parts. So you define a module once and you can instantiate it multiple times throughout your design. So much like using the same chip in different places on the circuit board. So modules can also contain other modules enabling hierarchical design, which is the key principle in complex hardware development. So every Verilog module follows a clear, consistent structure. So you start with the module keyword and you give your block a unique name. So inside the parenthesis, you list all the ports. So these are the signals used to communicate with other modules. After the header, you will declare the ports with their directions like input, output or inout. Then you need to define internal signals using wire or ridge. Like the actual functional logic, it can be continuous or procedural logic. Optionally, you can even instantiate other modules inside, creating a hierarchy. Finally, close the definition with end module. So this structure becomes very handy after writing few of the modules. So it is the skeleton that every Verilog design is built on. Now that we know what module is, let's look at how it connects with the rest of the system through ports. So in Verilog, there are three port directions. Input, the data comes into the module, and output, data is sent out from the module, and inout, used when signal needs to travel both ways, like a data bus. So most modules will only use input output. Inout is powerful but rare and often avoided in synthesizable design because of its complexity. In the next slide, we will talk about how these ports are declared in different styles like ANSI and non-ANSI style. So let's move on. So there are two main styles to write Verilog module headers, ANSI and non-ANSI. So the ANSI style is newer and much easier to read. It combines the port list and direction declaration in one place. That makes your code more compact and readable. And it's what you will see in most of the modern designs and tutorial. The non-ANSI style separates the port list from the direction declaration. It is older and more verbose, but it is still supported. You may see it in the legacy code or academic materials. So for beginners and even in industry, ANSI style is the highly recommended. It is cleaner, quicker and less error prone. Next, let's look at the complete example module to bring it all together. Now let's put everything together in a real Verilog example, a simple 2-input AND gate. So we define the module with the module keyword and we use ANSI style port declaration right in the header. So inside the module, we use an assign statement to perform the logical operation. So this is called continuous assignment and it is typically used for combinational logics like this. Even though it's a simple circuit, the structure we used like modules, ports and logic is the same format used in more complex designs also. So in the next few slides, we will learn how to reuse this module inside another module by instantiating it. So far, we have learned how to write a module, but how do we use it inside another design? That's where module instantiation comes in. So think of your Verilog module like an integrated circuit. So you design it once and then you can plug it into a bigger circuit as many times as you want. So in Verilog, this is exactly what instantiation allows you to do. It's how we achieve hierarchical design. So building a large systems from small and manageable components. In the next two slides, I will show you the two ways to instantiate a module using positional and named mapping. This is the positional mapping method of instantiation, where connections are made based on the order of ports in the module definition. Let's say the original module has a ports A, B, Y in that exact order. So when you instantiate it, the first signal connects to A, the second to B and the third signal to Y. It's a quick method and works well for simple modules with 2 or 3 ports. But as your design grows, positional mapping will become risky. If you accidentally mix up the order, you might connect the wrong signal without even realizing it. That's why many engineers prefer named mapping, which we will see next. Now, here's a much safer and clearer way to instantiate your modules, that is named mapping. Instead of relying on position, you match the module's port names with the signal names explicitly using a dot notation. For example, dot A in the bracket input 1 connects the module's port A to the signal input 1. This has several advantages. It is easy to read, you don't have to remember port order, and it avoids subtle bugs, especially when your port list is long. For these reasons, named mapping is considered a best practice in the professional Verilog development. Up next, we will look at the real-world analogy to help you solidify your understanding of modules and instantiation. Let's break down the concept of modules and instantiations with a real-world analogy. Think about building your own computer. You have different components like CPU, GPU, RAM. Each one does a specific job. So these are just like a Verilog modules. Each part has a connectors like power pins, USB ports, data buses. And these are like the ports of your module. When you assemble your PC, you plug those parts into the motherboard. So when you assemble your PC, you plug those parts into the motherboard, and that's exactly what instantiating a module means in Verilog. So even better, if you need more RAM, you just add another step. So similarly, in Verilog, you can instantiate the same module multiple times with the different connections. I hope this analogy helps you to understand how a modular and scalable hardware design is with Verilog. And that wraps up our video on Verilog modules, ports and instantiations. Now you know how to write a Verilog modules, declare ports the cleaner way and instantiate them inside another module. So in our next video, we will dive into Verilog data types, where you will learn the difference between wire, register, integer and more, and how they play a role in simulation and synthesis. So make sure to like this video, subscribe to our channel and drop your thoughts or questions in the comments. So this is VLSI Simplified. See you in the next video. Bye.